So, good afternoon everyone. I am Ankara Kartika. Let us wait 2 more minutes for others to join and then we'll start the session. Okay, we'll start now. Um, Myself Ankara from the Department of Chemical Engineering, IIT Hyderabad, has been handling these problem solving sessions for the NPTEL course Fluidization Engineering. So the course is a 12 weeks course and the course instructor is Professor Subrata K Majumder from the Department of Chemical Engineering, IIT Guwahati. So today is Saturday session. If you have any difficulty from my end in terms of my audio or my screen, please let me know. And also the call is open to all, so even if there is any internet disruption, I'll be joining back the call in 2-3 minutes. So please wait for the time being in the call, because you can be in the call without my presence as well. So that is one thing I want to add. And if at any point you feel that you are saying something and I am not audible, put it in the chat window so we can discuss at the end also. And I have, in today's class, I have kept my audio also full, and I hope you people are able to hear me as well. So these are the points to have a smooth session. In between, if you have any other things to add on, or let me know. So now let us move on to today's session. So this is a course layout. So as we have seen, this is a 12 weeks course. So by now we have covered almost 6 weeks, and in this we have seen the introduction to fluidization and how we are classifying the solids, and also the flow pattern inside the systems, like also the governing frictional pressure drop and models to study them, and also type of gas distributor also we have seen, and also we have seen about the bubbling fluidized bits in the last class. So bubbling fluidized bits itself is an interesting concept, because in most gas solid fluidized bits bubbles play an important role. You need to understand how the bubbles are forming and how large they can go in size, and so many things, how much they can carry over the solids. Because of these aspects, the hydrodynamics inside the bed is being affected. So it becomes important for us to know how bubbles behave inside the fluidized beds. Especially in gas solid fluidized beds, the bubble dynamics is an important study, And in later classes, we'll be studying about entrainment, elution, aeration, heat transfer, mass transfer phenomena, and also mixing behaviors inside the bed. So let us move on to today's class, in which we are dealing with the bubbling fluidized beds. So before that, for the books and references, the first one is Cooney and Levenspil's Fluidization Engineering. It is always good to read this book if you want to have a complete understanding of the fluidization concepts. All the things covered related to basics of fluidized beds to an advanced level as well. Uh, the recent aspects might not have been covered, but all things that we need to know is covered in this book. And next one is Gidaspo's multiphase flow and fluidization, continuum and kinetic theory description. Again, this is an important book in which it is the covered in terms of the modeling aspects of fluidization is also covered in addition to the basics of fluidized beds. And third one is Giblaro's fluidization dynamics, and last one is K Majumder's hydrodynamics and transport processes of inverse bubbly flow. So now let us see bubbling fluidized beds. Why do we need to study the bubbling fluidized beds? Because the movement of solids is being different in the bubbling fluidized beds. For example, if you see the flow pattern of movement of solids inside the bubbling fluidized beds, it is different in terms of the way in which they go. And also this particular thing depends on the aspect ratio of the bed. Here z by dt is equal to 1, and again here both the bed dimensions are the same, but at low velocity the flow of solids is from the near the perimeter to the center, while at higher velocity the flow of solids is from the center to the near the walls. So here it is from walls to the center, while here it is from center to the walls. And at a z by dt ratio of 2, where z denotes the height of the bed and dt denotes the diameter of the bed, here you can see that the velocity is high, but the movement of solids is kind of like from the near the walls at the bottom, and it goes to the top, and here the circulation is there, and some of the solids are also thrown over to the walls from the center at some height. And this is general pattern in deep beds. Okay, in a knot. This one is the deep beds. Like here you can see that this one is a deep bed, but more deeper beds. Like these, here you can see the height is very much tall. Height of the beds is very high compared to the diameter of the bed, and the motion of the solids is such that here one circulation pattern you are able to see. Apart from that, the solids are also going to the higher heights, and it is reaching to the walls. That is, they are going towards the going to the top from the center of the bed, and it is getting thrown. Like so many circulation patterns we are able to see. This is in deep beds. This is the general pattern that is occurring in most deep beds. If the bed is shallow, that is their height is very low compared to the diameter of the bed, we are able to see different circulation zones. Here the solids movement is this one, and also here it is in this way, like circulation is differing. And this is again a shallow bed wherein we are able to see tears. So even tears, presence of them affects the movement of solids. Like here, because of the airflow, they are taken up, but again they are in circulation in between the tears. So that is the concept behind the need to study bubbling fluidized beds, because these solids are carried to the top because of the inlet fluid and the bubble formation also. So movement of solids in bubbling fluidized beds in turn depends on the fluid velocity and bed dimensions also, like in terms of its height and diameter. So that is the thing over here. Let us now move on to the problems. The question 1: under the aggregative fluidized bed, the bed consists of dash bubble phase, emulsion phase, both A and B, slug phase. So I would like to remind you that in today's class of fluidization engineering related to public fluidized beds, the almost all the problems are mostly theoretical problems. Problems are being asked less. That is the numerical problems are less, but mostly conceptual problems are discussed in this week's assignment. So let us see that. Under the aggregative fluidized bed, the bed consists of bubble phase and emulsion phase. So we must all know that it consists of both bubble phase and emulsion phase. So both A and B is the right answer because it is an aggregative fluidized bed. So we have the presence of a bubble phase as well as the emulsion phase. So answer is option C. Both A and B is the right answer. Now let us go to question 2. In question 2 it is given that if the number of orifices per unit area is NOR, then for equilateral array of holes is dash. So here if the number of orifices per unit area is NOR, that is number of orifices per unit area. So what is the number when it is for equilateral array of triangular array of holes? So if it is equilateral triangular array of holes, what is the value? That is what is being asked over here. And here we must be careful to understand the question is regarding equilateral triangle array of holes, and it is not square array of holes. So for equilateral triangle of holes we need to see, and in NOR is the number of orifices per unit area, and LOR is the spacing between the adjacent holes. So if NOR is nothing but the number of orifices per unit area, if you are taking 1 meter square, the number of orifices inside that area is NOR, and the spacing between two orifices, the distance between two orifices is given by LOR. So now let us see options. The first one is NOR is equal to 2 by square root of 3 LOR square. And second one is VB is equal to 1.378 G 1.4 by G 0.6. And C NOR is equal to 2 by square root of LOR square. And last NOR is equal to 1 by square root of 3 LOR square. So as far as we are concerned, we are going to see what is the correct option for equilateral triangle array of holes. So the right answer is NOR is equal to 2 by square root of 3 LOR square. Answer is option A is the right answer. Option A is the right answer. Yeah. So NOR here, the question might come from square array of holes also. So you must be careful to read the questions before choosing the options. That is one thing. Now let us go to questions 3. Oops. Oh, weird. I have missed one question, I think. According to Davidson and Harrison 1963, the bubble volume at low gas flow rate can be expressed as dash. According to Davidson and Harrison 1963, the bubble volume at low gas flow rate can be expressed as dash, where VB is the bubble volume, G is the volumetric gas flow rate, and G is the acceleration due to gravity. So Davidson and Harrison 1963 model, what is the bubble volume? VB is equal to dash. So let us see the options. Option A, it is VB is equal to 1.378 into G to the power of 1.2 divided by G to the power of 0.6. Option B, VB is equal to 1.378 G to the power of 1.4 divided by G to the power of 0.6. Option C, VB is equal to 1.378 G to the power of 1.2 divided by G to the power of 0.7. And last option, it is VB is equal to 1.378 into G to the power of 1.2 divided by G. So again, it is a conceptual question which is asking what is the correct equation for finding the bubble volume according to the Davidson and Harrison 1963 model. So we all know it is G 1.378 into G 1.2 divided by 1.6 is the right answer. So this one is the right answer, option A. So yeah, option A is the right answer. Now let us go to question 5. In question 5, the general expression for solder mean drop diameter D32 is dash, where D32 is the solder mean drop diameter and DD is the drop diameter and Ni is the number of drop of diameter DD. So the question is regarding identifying the correct expression for solder mean drop diameter D32. So D32 is solder mean drop diameter, and in the expression some other terms are also present like DD, which is nothing but the drop diameter, and Ni, which is nothing but the number of drops of diameter DD. So now we are going to look at the options and finalize the answer. Option A, it is D32 is equal to summation of Ni into DD4 from I is equal to 1 to n divided by summation I is equal to 1 to n Ni dd square, and option B, it is D32 is equal to summation of I is equal to 1 to n over Ni dd cube divided by summation of I is equal to 1 to n Ni dd square, and option C, it is D32 is equal to summation of I is equal to 1 to n Ni dd cube divided by summation of I is equal to 1 to n divided by Ni square dd square, and summation option D, it is D32 is equal to summation of I is equal to 1 to n dd cube divided by summation of I is equal to 1 to n Ni square dd square. So yeah. So if anyone knows the answer, you can unmute yourself and answer, or else because it is a simple question. Similar questions we have been seeing from first week, so I assume you people should be knowing this by now very confidently and very clearly. Okay, the answer is actually option B, that is D32 is equal to summation of I is equal to 1 to n Ni d cube, it is cube in the numerator divided by summation of I is equal to 1 to n in Ni dd square. So square in the denominator, 3 in the numerator, square in the denominator. So option B is the right answer. The thing to be noted over here is that in most cases, if it is 3 and 2, the options, then the answer would also be similar thing in the numerator and denominator. In most cases, it would be the case, but please verify when you are dealing with such problems and make sure that is right. But the general observation from my end is that, and so option B is the right answer. Option B, D32 is equal to, that is solder mean drop diameter is D32, that you must know. Solder mean drop diameter is known over as D32, and D32 is nothing but summation of I is equal to 1 to n Ni into dd cube divided by summation of I is equal to 1 to n Ni dd square. So that is for the question 5. Now let us go to question 6. In question 6, it is given that with an increase in pressure, the bubble size, without options itself, we should be knowing that the bubble size decreases. When the pressure inside the fluidized bed is increased, the bubbles will be shrinking in size, and therefore their size will be reduced, and also their they will be broken down actually. That is the thing. With an increase in pressure, the bubble size actually decreases. So let us now look at the option. Option A increases. Option B, it is decreases. Option C remains the same. Option D, all of these. It cannot be all of these and it cannot be increases. In general, if you are increasing in size, increasing in pressure itself, that pressure will actually break down the size of the bubbles, and these bubbles will shrink in size. Though therefore the right answer is it decreases. Option B is the right answer. So option B is the right answer. With an increase in pressure, the bubble size decreases. I hope it is clear now. We'll go to next question, question 7. In question 7, the initial bubble that formed at the end of the jet from orifice is expressed as dash. So the initial bubble that formed at the end of the jet from orifice is expressed as dash, where dB naught, dV, Uj are initial bubble diameter, and jet velocity. The initial bubble that formed at the end of the jet from orifice is expressed as dash. In that option, dB naught is nothing but initial bubble diameter, dB is the bubble diameter, and Uj is the jet velocity. So dB naught by dB is equal to 0.41 into Uj 0.375 divided by dB 0.25. Option B, it is dB naught divided by dB is equal to 0.51 into Uj power 0.375 divided by dB power 0.25. Option C, it is dB naught by dB is equal to 0.41 into Uj power 0.95 divided by dB power 0.25. Option D, it is dB naught by dB is equal to 0.41 into Uj power 0.375 divided by dB power 0.15. So these are the things. In addition to that, here we need to identify first the right answer. The answer, I can say it is 0.375, 0.25 and 0.41. I mean the answer involves these three numbers. From that I can see the answer is actually option A. So dB naught by dB is equal to 0.41 into Uj power 0.375 divided by dB power 0.25. So the answer is option A. So here we asked the question relating to how the initial bubble would be. So the initial bubble formed at the end of the jet from orifice is expressed as dash. In that, dB naught is equal to dB into 0.41 into Uj power 0.375 divided by dB power 0.25 is also the way to write. But please make sure that numbers in the equation is right, because these numbers are given in the options are very closely related. It would be difficult. Like assignment problems you can solve because it would be fresh in your mind from where you have read, but in the final exam it might be difficult. So please make sure that you are aware of the numbers in the equations. So answer is dB naught by dB is equal to 0.41 into Uj power 0.375 divided by dB power 0.25. So that is question 7. Now let us go on to question 8. In question 8, it is given that according to Cunha and Levenspiel, the value of bubble frequency is generally in the range of dash. So answer is option, let us look at the options first. A 10 to 5 per second, 15 to 25 per second, 19 to 12 per second. Option D, it is 15 to 20 per second. So what are they asking? According to Cunha-Levenspiel. So this is in according to the Cunha-Levenspiel's model, and we are asked to find the value of the bubble frequency. So the bubble frequency is the number of bubbles per second. So actually they propose an equation, and after fitting the number of things, the answer we arrive at is option C, that is 19 to 12 per second is the right answer. So again this is directly from the concept. So you would be aware of the answers by now. So answer is option C, 19 to 12 per second. So that is the answer. Now let us go to question 9. In question 9, it is given that the single rise bubble velocity in liquid for a long bubble in the tube is dash. So the question is single rise bubble velocity in liquid for a long bubble in the tube is dash. And in that particular equation, UBR represents the single rise bubble velocity, BR that is bubble rise velocity and for a single bubble, and G is the acceleration due to gravity, and d bed is the diameter of the bed. So the question is asking the single rise bubble velocity in liquid for a long bubble in the tube is dash. So again I think we are asked to find the formula. Yes, so option A, it is UBR is equal to 0.35 into G power minus 0.5 dB, I mean diameter of bed power 0.5. And option B, it is single rise velocity UBR is equal to 0.35 into square root of G, that is acceleration due to gravity, into diameter of the bed. And option C, it is UBR is equal to 0.65 into square root of G into diameter of the bed. And option D, it is UBR is equal to 0.35 into square root of G square into D bed. And option E, again it is UBR is equal to C into G power 0.4 into VB power 1 by 6. So single rise bubble velocity is in liquid for a long bubble in the tube is asked. So answer is UBR is equal to 0.35 into square root of G into dB. I mean diameter of bed is the right answer. So here the answer is answer is option B. So in question option A, it is, even though it is diameter of the bed, G is given in the denominator, so this one is false. Whereas option B is the right answer. And option C, the coefficient is different, and in option D, it is given with square. So the options would be confusing, so please pick the right option from the question. So answer to this particular question is option B. UBR, that is the single rise bubble velocity in a liquid, is equal to 0.35 into G d bed into square root of G into d bed, where d bed denotes the diameter of the bed and G is the acceleration due to gravity, and UBR is the single bubble rise velocity. Single rise bubble velocity. The answer is option B. Now let us go to question 10. In question 10, the wall effect predominated when equivalent bubble diameter is dash. Option A, more than 1 by 4 of bed diameter. Option C, less than 1 by 4 of bed diameter. Option C, same as bed diameter. Option D, none of the above. The wall effect predominated when equivalent bubble diameter is dash. So when bubbles are growing in size inside the bed, there will be smaller bubbles and there will be larger bubbles. So the presence of walls, that is the bed walls, will pose some effect in the bubble size and everything. So when does that happen? So for a smaller bubbles, the small effects would be less and it would not be affecting the bubbles very much. But for larger bubbles, the bubble size will be matter. I mean, it would be it will be it matters, and so therefore we need to know at what size the bubble size, at what size of the bubbles the wall effect comes into picture. So as we have seen that in slugging bed also, like the bubbles will be growing in size and they almost reach the size of the column, like that we have seen. So here after a certain size of the bubbles, the wall effect comes into picture. So the question is regarding at what size of the bubbles should we consider the wall effect. So answer is actually option A, more than 1 by 4 of the bed diameter. So option A is the right answer. In general, it is like 1/3 of the bed diameter. After that, the wall effect comes into picture, but it is close relation. So more than 1 by 4 of the bed diameter. So if bubble sizes are less than 25% of the bed diameter, bed size, the wall effects will also be coming into picture. So we should include the effect of wall on the bubble size, bubble motion, everything when we are dealing with the bubble dynamics inside the bed. So answer is option A. The wall effect predominated when equivalent bubble diameter is more than 1 by 4 of bed diameter. So now let us go on to question 11. The general equation for bubble rise velocity is dash. The general equation for bubble rise velocity is dash, where UBR is the bubble rise velocity and C is a constant, G is the acceleration due to gravity, and VB is the bubble volume. So again we are asked to find the proper equation for the bubble rise velocity. In this particular equation, the terms appearing are UBR, that is the bubble rise velocity, and C is a constant, G is the acceleration due to gravity, and VB is the volume of the bubble. So first option A, it is UBR is equal to C into G VB power 1 by 6, and option B, it is D UBR is equal to C into G power 0.5 VB power 1 by 6, and option C, it is UBR is equal to C into G power 0.5 VB power 1 by 3, and option D, it is UBR is equal to C into G power 0.4 into VB power 1 by 6. So the answer I think is option B. Yeah, answer is option B. UBR is the bubble rise velocity and C is a constant, G is 1.5 and VB is 1 by 6. So please be careful of the coefficients and also the power terms in the equation. So the questions might come like this and you should be very much confident of those exponent terms and coefficient terms. So in this particular question, it is about finding the bubble rise velocity, and I myself got confused with this slightly. But UBR is equal to C into G power 0.5 VB power 1 by 6. So that is the answer, and yeah, option B is the right answer. Now let us go to question 12. In question 12, it is given that the hydraulic diameter of the bed can be calculated by dash, where d bed h is the hydraulic bed diameter. So actually thing is that you will be calculating the bed diameter, I mean using the bed diameter in most of the calculations, and hydraulic diameter of the bed can be calculated by dash. So if there are internal features in the fluidized beds like tubes will be there for efficient heat transfer mechanisms or something, there will be some things inside the bed like tubes and some anything will be there in some situations. So if they are present, how can we calculate the hydraulic diameter of the bed? So we need to identify the formula for that. So let us look at the options. Option A, it is d bed h, that is the hydraulic diameter is equal to 4 into cross sectional area available to fluidized beds divided by total wetted perimeter of bed and tube. And B, it is hydraulic diameter for the bed is equal to total wetted perimeter of the bed and tube divided by cross sectional area available to fluidized bed. Option C, it is 4 into total wetted perimeter of bed and tube divided by cross sectional area available to fluidized bed. And option D, it is hydraulic diameter of bed is equal to total wetted perimeter of bed and tube divided by cross sectional area available to fluidized beds. So now answer to this particular question is actually option A, where hydraulic diameter of the bed can be given as 4 into cross sectional area available to fluidized bed divided by total wetted perimeter of bed and tube. So this is the way we would be, we mostly do the calculation for getting the hydraulic diameter, that is 4 into cross sectional area divided by some wetted perimeter. In general, we calculate the hydraulic diameter by that. So even here we are calculating it as 4 into cross sectional area available for fluidized bed divided by wetted perimeter of bed and tube. As I mentioned, like there is a presence of tubes or some internal features So because of that, we are required to calculate the hydraulic diameter of the bed. So in that case, we use this particular formula. Now, apart from the theory behind the question, there is one more thing in this particular question, how we can eliminate the options. The dimensions of the diameter of the bed, that is the hydraulic bed diameter, is meter or centimeter, that is length unit, right? 4 into cross sectional area unit is length square divided by perimeter, perimeter is length, so length square by length is giving length. So here it is option A, it is dimensionally correct. Whereas in option B, C and D, if you look at it, we can see that total wetted perimeter divided by cross-sectional area available to fluidized beds. So here the 4 is in denominator, here in numerator, here in 4 is absent. But if we neglect the coefficient, I just want to give you an idea, like if you are in some cases it would not be available for all problems, obviously, but here it is length by length square, length by length square, length by length square. So what is the unit we are getting? We are getting 1 by length. Whereas in the LHS left hand side we are having L. So LHS is not equal to RHS for the dimensional equality. Dimensionally, these equations are inconsistent as well. So in that case also, by that means also you can eliminate option B, C and D. So the right answer is actually option A. D bed, that is the hydraulic diameter of bed, is equal to 4 into cross-sectional area available to fluidized bed divided by total wetted perimeter of bed and tube. So option A is the right answer. Diameter of hydraulic diameter of bed, D subscript bed H is equal to 4 into cross sectional area available to fluidized bed divided by total wetted perimeter of bed and tube. So now let us go to question 13. Okay, question 13 is a problem, that is numerical problem. What is asked? The fluidized bed reactor is packed with silica alumina catalyst, where air was used as a fluidizing medium. Diameter of the reactor is 0.45 meter. Calculate the diameter of bubble size from the bed distributor height of 0.4 meter. Near the inlet of the air distributor, the maximum bubble diameter observed was 1.3 mm. The maximum diameter of bubble was 4.2 mm. So what is asked, that we have a fluidized bed and consider this is the distributor, gas distributor. Here we are passing air inside the fluidized bed and diameter of the reactor, that is diameter of the fluidized bed, is 0.45 meter. This is the D bed or dB, whatever it is we are using, we will see that later. Calculate the diameter of bubble size from the bed distributor height of 0.4 meter. So from here, let us assume it is 0.4 meter height. Height is equal to 0.4 meter. At this particular height, what is the diameter of bubble? Okay, this won't be dB. This is dB is mostly used for bubble diameter. What is the bubble height at a height of 0.4 meter? And what else is given? Near the inlet of the air distributor. So here the max bubble diameter is 1.3 mm. So dB naught is 1.3 mm and maximum bubble diameter was 4.2 mm. So in general, the maximum bubble diameter was dB max is equal to 4.2 mm. So what is asked? We are given the dimension of the bed, diameter of the bed, that is 0.45 meter, and we are using air as the fluidizing medium. So obviously we will be getting bubble formation, and maximum diameter of the bubble in the bed is given as 4.2 mm, and in of the air distributor, maximum bubble diameter was given as 1.3 mm. And we are asked to find the diameter of the bubble at a height of 4.4 meter. So we are asked to find the bubble diameter size, bubble diameter at the height of 0.4 meter, whereas we know the maximum bubble diameter size at the near the inlet of the air distributor, that is 1.3 mm, and the maximum diameter of bubble inside the bed as 4.2 mm. So, and what else is given? Yeah. So now let us look at the options, and it is option A 2.36 centimeter, option B it is 1.304 mm, and option B it is 2.003 mm, and option C it is 3.521 centimeter. Obviously the bubble diameter size would not be in centimeter, because the maximum bubble size observed was itself 4.2 mm. So we can eliminate option A and D actually, and we are now left with option B and C. Both are greater than the bubble size at the inlet, and but less than the maximum bubble size, that is greater than 1.3 but less than 4.2. So now we should see how we are getting, and we are actually calculating the bubble diameter at a height of 0.4 meter. So by looking at it, we can say that answer is actually option C. But now let us see how to solve it step by step. Option C is the right answer. So when we are looking at it, solution, we find that, let us first write what is given. So given things is the diameter of the reactor, that is D bed, is given as 0.45 meter, and maximum bubble diameter observed near the inlet of the air distributor is 1.3 mm, and maximum diameter of bubble size is dBm is 4.2 mm. So dB naught and dBm is given, diameter of bed is given. So what are we asked to find? We are asked to find the diameter of bubble from the bed distributor of height of 0.4 meter. So what is the formula? Okay. Formula is dBm minus dB is divided by dBm minus dB naught is equal to E to the power of minus 0.3 Z by D bed. So here dBm is maximum bubble diameter, and D bed is dB, that is dB is the diameter of the bubble which we need to find, and dB naught is the initial bubble diameter near the inlet of the orifice. So we can see that. So if you see that dB will be greater than dB naught. From the formula itself we can say that how, because E minus 0.3 Z by D bed. So obviously Z by D bed is coming as Z would be greater than, Z is the height at which we need to find the diameter of the bubble size. So Z is the height at which we are asked to find the diameter of the bubble, and D bed is the diameter of the bed. So mostly it would be a fraction. So if it is a fraction, denominator is actually higher than numerator. So if numerator is smaller, dB should be larger than dB naught. So we'll substitute these things. So dBm we know it as 4.2 mm, and dB we need to calculate, and divided by 4.2 minus 1.3, that is dB naught is 1.3, is equal to E into minus 0.3 into Z, that is the height at which we are asked to find the diameter of the bubble. So it is 0.4 divided by 0.45, that is the diameter of the bed. So from this we are getting it as 1.98 mm. So it is actually round off to 2. Some calculations points would be missed out over here. But the takeaway is that we are asked to calculate the diameter of the bubble at some specific height. Let us say the height as Z. So dBm is given as the maximum bubble size inside the fluidized bed, which is 4.2 mm, and dB is the diameter of the bubble at a specific height z. In this particular formula, dB is the diameter of the bubble at height z, and dB naught is the maximum bubble diameter observed near the inlet of the distributor. So dB naught is 1.3, and dBm is the maximum bubble size inside the bed, which is 4.2. dB is unknown, and z is the height at which we are asked to find the bubble size, that is 0.4 height from the bottom gas distributor, and d bed is the diameter of the bed. So all things are given and it is just a direct substitution. So we are getting us 2 mm. So if we go back and look at this, we are getting actually 2.0 mm. So it is in mm. So our answer is actually option C. What is asked: if the fluidized bed reactor is packed with silica alumina catalyst and air was used as a fluidized medium, and diameter of the reactor is given, and diameter of bubble size we are asked to find from a certain height 0.4 meter, and we are given the inlet of the air distributor and maximum, no, near the inlet of the air distributor the maximum bubble size is given, and maximum bubble size inside the bed is also given. So we have just substituted in this particular formula and we got the right answer. So dB we have found out as 2 mm. So that is this particular question. Now let us go on to question 14. According to Choi et al. 1998 model for the bubble coalescence frequency dash, bubble moves upward. Option B, bubble speed remains constant. Option C, time average movement of bubble movement. Option D, all of these. So actually, according to Choi et al. 1998 model, the bubble coalescence frequency is dash. So their model actually says that the calculation assuming that the bubble is moving upward, and bubble size remains, bubble speed, that is bubble motion speed remains a constant, and time average movement of the bubble movement will be considered over there. So from these aspects bubble coalescence frequency is found out. So answer is actually all of these is the right answer. That is according to Coeter model 1998 model, bubble moves upward and bubble speed remains constant. Time average movement of bubbles is considered. So that is all of these is the right answer. Now let us go to question 15. In question 15 it is asked that if the bubble rise velocity and bubble diameter is 4 mm per second and 0.25 mm respectively in fluidized bed, what will be the bubble coalescence frequency per unit volume? Number of bubbles produced per unit volume is 5. So what is given? Bubble rise velocity is given as 4 mm per second and bubble diameter is given as 0.25 mm. So bubble rise velocity is given as 4 mm per second and bubble diameter is 0.25 mm inside the fluidized bed. So what is the bubble coalescence frequency per unit volume? And if the number of bubbles produced per unit volume is 5. So here the bubbles are coalescence, bubbles coalescence is considered, and what is the bubble coalescence frequency per unit volume? Given that we know the bubble rise velocity and bubble diameter and the number of bubbles produced per unit volume. So these three things we know and we are asked to find the bubble coalescence frequency per unit volume. So let us see the options first. It is 11.10 second, 11.10 per second and 12.16 per second. Option C, it is 9.17 per second. Option D, it is 16.26 per second. If the bubble rise velocity and bubble diameter is given, what is the bubble coalescence frequency per unit volume? And number of bubbles produced per unit volume is 5. So answer is actually option A, but we'll see how to do the calculation first. So it is question 15 solution. What is given? We are given the bubble rise velocity 4 mm per second and bubble diameter 0.25 mm, and number of bubbles produced per unit volume is 5. So what are we asked to find? We are asked to find the bubble coalescence frequency per unit volume, and formula is FCV, that is the bubbles coalescence frequency per unit volume is equal to 0.5658 into pi into dB square into VB into N square. So everything is straightforward actually. It should be, I think, VB, small VB. Okay, it is pi 0.5658 into pi into dB square. dB is the diameter of the bubble and VB is the bubble rise velocity and N is the number of bubbles produced per unit volume. So actually it shouldn't be. I mean, large VB mostly denotes the volume. That's why I changed it to smaller V. So we are substituting everything in the equation, from which we are getting FCV is equal to 0.5658 into pi is 3.14 into dB, that is diameter of the bubble is 0.25 the whole square, and into VB, that is bubble rise velocity, is 4 into N, that is the number of bubbles produced per unit volume, which is 5. So N square, so it is 5 square. So what are we getting? 11.1038 per second is what we are getting. So going back to the question, it is okay, 15 question. If bubble rise velocity and bubble diameter is given as 4 mm per second and 0.25 mm respectively in a fluidized bed, what will be the bubble coalescence frequency per unit volume when the number of bubbles produced per unit volume is 5? So answer is actually 11.10 per second. Option B, C and D are 12.16, 9.17 and 16.6 per second respectively. But we have calculated and we are getting the answer as 11.10 second as well. So answer is option A. How did we do? We are written the given and to find bubble coalescence frequency per unit volume. And formula is FCV is equal to 0.5658 into pi into N square into dB square into VB, where dB is the diameter of the bubble and VB is the bubble rise velocity and N is the number of bubbles produced per unit volume. So we are just substituting everything in the equation and we are getting the answer. The challenge is to remember all the equations in fluidization because there will be a number of equations. You need to know the proper coefficients and exponents in some terms. So that would be a challenge. But apart from that, the numerical problems are really simple. You just need to substitute the values in that equation and get the right answer. So please make sure to remember the formula perfectly. So that is this question. We now go on to question 16. In question 16, it is asked that in a fluidized bed regime, the influence of wall effect is dominant in a single bubble, option A single bubble regime, option B slugging regime, option C turbulent regime, option D fast fluidization. I think slugging. In a fluidized bed regime, influence of wall effect is dominant in dash. So option A it is single bubbling regime, option B it is slugging regime, and option C it is turbulent regime, and option D fast fluidization. So while studying the fluidization regimes itself, we have seen that how bubbles grow very large in size in slugging regime and they almost reach the size of the column. So if bubble diameter is greater than 1/3 of the diameter of the column, we say that influence of wall comes into picture. So in this particular question, the question is regarding influence of wall effect is dominant in dash. So we obviously know the effect is predominant in slugging regime because in slugging regime the size of the bubble is almost the size of the column. Those bubbles keep on increasing in size, therefore slugging regime is the answer. Now let us go on to question 17. In question 17 it is given that for a lower liquid viscosity, bubble rise velocity inside fluidized bed depends on dash. For a lower liquid viscosity, bubble rise velocity inside fluidized bed depends on dash. Inertial force and surface tension. Option B, viscosity and density. Option C, gravity. Option D, buoyancy force. So lower liquid viscosity, bubble rise velocity actually depends on inertial force and surface tension. So answer is option A. Because the viscosity is lower, the surface tension plays an important role for the bubble rise velocity. So answer is option A. Question 18. It is about if the diameter of the bubbles inside the bed exceeds by 25% of the column of 25% that of column diameter, which one of the following is correct? Bubble velocity is affected by column wall. Bubble velocity is independent of column wall. Both A and B, none of these. Answer is bubble velocity is affected by column wall. Option A is the right answer. Because again here we are able to see that the diameter of the bubbles inside the bed exceeds by 25% of the column diameter. We have already seen in the previous question itself how at what diameter of the bubble the wall effect comes into picture. We have seen it as 1/4 of the diameter of the bed. So it is exceeding that 25%. So after 25% of the column diameter, if bubble size is increasing beyond, the wall effect comes into picture. Wall effect, how it was affecting the, by wall effect, what do we mean? It is affecting the bubble velocity. So answer actually is option A. Option A is the right answer. Bubble velocity is affected by column wall. Let us go on to question 19. In question 19, it is given that bubble rise velocity of a single bubble in a quiescent bed is expressed as dash, where UBR is bubble rise velocity, G is acceleration due to gravity, and VB is the bubble volume. So here the question is about rise velocity of a single bubble in a quiescent bed is dash. So let us look at the option first. Option A, UBR is equal to 0.71 into G power 0.5 VB power 1.6, and option B, it is UBR is equal to 0.75 G power 0.6 VB power 1.1/6. Option C, it is UBR is equal to 0.31 G power 0.5 VB power 1/6. Option D, it is UBR is equal to 0.46 G power 0.6 VB power 1/6. So answer is, as we all know, it is option A, I guess. Yeah, UBR, that is the bubble rise velocity, is equal to 0.71 times square root of G, that is acceleration due to gravity, G to the power of 0.5 into VB, that is the bubble volume, to the power of 1/6. Rise velocity of a single bubble is 0.71 into G to the power of 0.5 into VB to the power of 1/6. So the terms in the equations are 0.71, 0.5 and 1/6. So in basics, UBR depends on G, that is acceleration due to gravity, and bubble volume. But what is the exact equation? UBR is equal to 0.71 into G to the power of 0.5 into VB to the power of 1/6. So answer is option A. So question 20, it is about the absolute bubble rise velocity in a swarm of bubbles is dash. The absolute bubble rise velocity in a swarm of bubbles is dash, where UBR, A, U and UBR are the swarm bubble rise velocity, gas velocity and bubble rise velocity. So here it is, instead of a single rise bubble, we are having a swarm of bubbles. So what is the absolute bubble rise velocity for that? That is UBRE, swarm bubble rise velocity is dash. In the particular equation, we have terms involving UBRE, which is the swarm bubble rise velocity, and U, it is the gas velocity, and UBR, it is the bubble rise velocity. So let us look at the option first. Option A, UBRA is equal to U minus UBR. Option B, UBRA is equal to U minus UBR plus 1. Option C, UBRA is equal to U plus UBR. Option D, UBRA is equal to U plus UBR minus 1. Actually, the equation comes in the form of that UBRA is equal to U naught minus UMF plus UBR. So if we take the equations alone, we have UBRA is equal to U plus UBR. So here UBRA is the swam bubble rise velocity and U is the gas velocity, or UBR is equal to bubble rise velocity. So answer is option C. Option C is the right answer. UBRA is equal to U plus UBR. So actually the time now is 4:02. Let us just take a 5 minutes break. Not even 5 minutes, give me 3-4 minutes. I'll be back by 4 minutes and we'll continue the session. So we'll start. So we'll start now. Okay, till now we have seen the problems related to week 6 problems. So this is week 5's problem. So just to some more problems and get you the answer and why that is so and so. So now let us look at it. Okay, the first one, shortcomings associated with laboratory scale distributor for the industrial operations. High pressure drop. Option B, high construction strength and low cost for some materials. And option C, it is high resistivity against thermal stresses and low cost for some materials. Option D, all the above. So what is the question is that when we are using laboratory scale distributors for the industrial operations, we cannot use that because it possesses some shortcomings. So what are they? The first one, it is high pressure drop. High pressure drop, this is true because when we are using the things we use in laboratory scale at such high scales, it will be creating high pressure drops, and because of that it will increase the pumping cost and overall cost will increase. So option A is true. When we look at option B, high construction strength and low cost for some materials, it if this happens, it is an advantage, it would not be a shortcomings. So this is false, and similarly option C is like a false. If there is a high resistivity against thermal stresses, it would be an advantage, it would not be shortcoming, but this is absent. So in general they offer low resistivity against thermal stresses and the cost for materials would be high. So answer is actually option A is the right answer, high pressure drop. We go to question 2. In question 2 it is given that perforated or multiporous plate distributor is dash. Laboratory scale distributor, industrial scale distributor, either A or B. Option D, none of the above. So these can be used in industrial scale as well. So it is industrial scale distributor. Question 3 it is, for the same orifice area and gas flow, which type of, so for the same orifice area and gas flow, which type of distributor on can cause large disturbances and give better mixing of particles? Perforated plate type distributor, nozzle tube type distributor, both A and B give identical mixing, none of the above. So for the same orifice area and gas flow, which type of distributor can cause large disturbances and give better mixing of particles? It should be nozzle tube type distributor. Option B is the right answer. Because like, why do we go for such complicated designs like nozzle tube type distributors? Because it for the same orifice area and gas flow, they are offering better mixing of particles than what we can get through perforated plate type distributor. So that is the advantage. So now let us go to question 4. In question 4 it is asked that the dead zone above the perforated plate shrinks with dash. Option A, increasing orifice and increasing particle size. Option B, increasing orifice and decreasing particle size. Option C, decreasing gas velocity and increasing particle size. Option D, none of the above. Answer is actually increasing orifice size and increasing particle size. Option A is the right answer. Dead zone is that where we cannot access the movement of the solids, the particles will be stagnant in those zones. So it is not preferable to have dead zones inside the fluidized bed. What can we do to minimize the dead zones or shrinking the dead zones? We can go with either increasing the orifice size. When we increase the orifice size, the zone where the particles would lay stagnant is minimized. And similarly, with increasing the particle size, also the stagnant zone is getting minimized, or else we can increase it in the gas velocity, again which would offer the particles to move, and it would not cause the particles to stay at a specific zone for a longer period of time, or else we can also decrease the spacing between the orifice. That is not given over here, but it is another fact which can do things to minimize the dead zones. What is that? We can increase the orifice size or decrease the orifice spacing, and also increasing the particle size or increasing gas velocity. The answer is option A. Option B, what is given, decreasing particle size, which is false, and option C, decreasing gas velocity, which is false. These two should have been reversed. So if that is the case, it would have been all the above. But since that is not the case, the answer is actually option A, increasing orifice and increasing particle size. Now let us see question 5. In question 5, the main advantage of bubble cap distributors are: option A, lower pressure drop. Option B, maximizes sweeping. Option C, higher pressure drop. Option D, none of the above. Lower pressure drop is one factor. If you look at option B, maximizes sweeping, it is not true. If that is the case, it is an disadvantage. And option C, higher pressure drop, again is a disadvantage. So answer is actually option A, lower pressure drop. So now we see question 6. It is given, which distributor is cheap and easy to fabricate? Perforated plate type distributor, Tewers type distributor, bubble cap distributor. Option D, all the above. It should be perforated plate type distributor. Perforated plates are like, you will have perforations inside the plate, and at the max it can be sandwiched between two meshes or something. But Tewers and bubble cap distributors, you need to have a special design and special construction. So B and C are complicated in design, so it is again not cheap. When it is complicated design, it is not easy to fabricate, nor it is easy. Nor it is cheaply available. So answer is actually perforated plate type distributor. Comparatively, it is cheaper and easier to fabricate. Therefore, it is option A is the right answer. Now let us see question 7. In question 7, it is given that main disadvantage of bubble cap distributors are dash. Difficult to avoid stagnant regions and not suitable for sticky solids. Option B, difficult to clean and difficult to modify. Option C, difficult in avoiding stagnant regions and expensive. All the above, it should be all the above. Yeah, because bubble cap distributors are difficult to clean actually, and difficult to avoid stagnant regions as well. And since it is difficult to avoid the stagnant regions and it is difficult to clean, and it is not suitable for sticky solids. Imagine it is getting stuck in some regions, it would affect the complete hydrodynamics inside the bed. It is not easier to use such beds, such solids in bubble cap distributors. So it is a disadvantage, and again it is difficult to clean and modify. And option C, it is difficult in avoiding stagnant regions, and it is expensive. In last slide itself we have seen bubble cap distributors are expensive because of its complicated design and difficulty in fabrication. So it is comparatively expensive, and option D, all the above. Therefore answer is all the above. We'll go to question 8. In question 8, it is given that which type of distributor prevents solids from falling through the distributor? Option A, perforated plate distributor. Option B, nozzle Tewar type distributor. Option C, bubble cap type Tewar type distributor. Option D, none of the above. Option B, option C. Okay. Option A, I mean, it is asking that which type of distributor prevents solids from falling through distributor. Like it should prevent the backflow of the solids or falling through the distributor. So when we look at option A, the chances of solids falling are there, and option B, nozzles are. It is chances are there for solids to flow over in nozzle tube type distributor as well. And in option C, bubble cap distributor, we have seen that it prevents the backflow of solids. Therefore, answer is actually option C, bubble cap tube type distributor. Now let us see question 9. In question 9, it is given that for the porous plate distributor, to maintain the uniform fluidization, pressure drop is related to fluid velocity such as required pressure drop is directly proportional to fluid velocity. Option B, required pressure drop is inversely proportional to fluid velocity. Option C, required pressure drop is proportional to the square of fluid velocity. Option D, none of the above. Here you should be very conscious of what the question is for what type of distributor. So to maintain the uniform fluidization, pressure drop is related to fluid velocity. Delta PD is in some way related to fluid velocity. That we know, but the relation is different for porous plate distributor and for perforated plate distributor. For example, in porous plate distributor, as in this questions, it is the pressure drop delta P is proportional to U naught. So answer is option A actually. Required pressure drop is directly proportional to the fluid velocity. But if the question is regarding perforated plate distributor, delta P is proportional to U naught square. It is proportional to square of fluid velocity. So be careful when you are dealing with such questions. For the porous plate distributor, to maintain the uniform fluidization, the pressure drop is related to fluid velocity such as required pressure drop is proportional to the required pressure drop is proportional to the fluid velocity. Because we are dealing with porous plate distributor, it is proportional to fluid velocity. But if it is related to the perforated plate distributor, it is proportional to the square of the fluid velocity. So be careful of what is asked. As for this question is concerned, it is porous plate distributor. So answer is proportional to the fluid velocity. Delta P is directly proportional to U naught. So answer is option A. Now let us go to question 10. In question 10, the jet will not contribute much to bed stirring and bubble rising when the factor alpha, which measures stirring effect, is dash. So here it is given that jet is not contributing much to bed stirring and bubble rising. So bed stirring, bubble rising, everything is related to kinetic energy, right? So what is the factor alpha? Alpha is the measure of stirring effect. So if you remember alpha formula, it is somehow related to kinetic energy. So if alpha is more, jets will, if bed stirring is there, kinetic energy is more and alpha should also be more. But if alpha is less, as in this particular concern question, what is that? Jet is not contribute much to the bed stirring. So bed stirring is less because jet is not contributing much. So alpha is again should be less. So alpha is very much less than 1. Alpha is very much greater than 1. Option C, alpha is equal to 1. Option D, alpha is equal to 0. So answer is alpha is less than 1. Option A is the right answer. If alpha is greater than 1, it contributes to bed stirring and bubble rising. So that is the thing. Now let us look at question 11. For the porous type distributor, to maintain uniform fluidization, pressure drop is related to fluid velocity such as. Why this question is being asked again, I don't know. Required pressure drop is proportional to fluid velocity. Required pressure drop is inversely proportional to fluid velocity. Required pressure drop is proportional to square of fluid velocity. None of the above. Maybe we can change the question actually. Why to put same question? Perforated plate type distributor. Now the answer is actually proportional to square of fluid velocity. So that thing. As we have seen, for perforated plate distributor, to maintain uniform fluidization, pressure drop is related to fluid velocity, such as required pressure drop is proportional to the square of fluid velocity. The answer is option C. Now let us go to question 12. In question 12, it is asked that if the factor alpha measures the stirring effect is lesser than 1, then jets will punch right through the bed, causing severe gas bypassing attrition of particles and erosion of bed materials. Option B, it is jets will not contribute much to the bed stirring and bubble rising. There is no particular jet formation, none of the above. As we have seen in the previous question itself, I don't know why the questions are being repeated and asked in different words. But if it is lesser than 1, jets will not contribute much to the bed stirring and bubble rising. But if it is greater than 1, it will punch right through the bed, causing severe gas bypassing and attrition of particles. So, but here the question is about alpha is lesser than 1. Alpha is measuring the stirring effect. So, the jets will not contribute much to bed stirring and bubble rising. So, answer is option B. Jets will not contribute much to the bed stirring and bubble rising when alpha is lesser than 1. So now we will see next question. Question 13. The ratio specific heat capacities gamma for the monoatomic gas is dash. Option A 1.33, option B 1.40, option C 1.67, option D 1.85. I think 1.4, 1.67. Okay, for monoatomic gas it is 1.67. Let us look at how. Ratio specific heat capacities, that is gamma. Gamma is nothing but Cp by Cv. Cp by Cv. So Cp is nothing but specific heat capacity at constant pressure, and Cv is specific heat capacity at constant volume. So the ratio of specific heat capacity at constant pressure to the specific heat capacity of constant volume is given by gamma, ratio of specific heat capacities, while for monoatomic gas it is dash. That is the question. For monoatomic gas, Cv is equal to F by 2R. So here for monoatomic gas, Cv is equal to F by 2R, where F is equal to 3. That is the translational degrees of freedom is there. 3 translational degrees of freedom. So Cv is equal to 3 by 2R, and Cp is equal to Cv plus R. Cp minus Cv is equal to R. So by that means if we calculate Cp, it is 3 by 2 R plus R. So it would be 5 by 2R. So now we need to find gamma is equal to Cp by Cv, and it is 5 by 3, it is 1.67. So I think it is clear now. So what are we dealing with? We are having Cp by Cv, we need to find out, and that is the ratio specific heat capacities. For monoatomic gas, we have 3 degrees of freedoms. So Cv is equal to F by 2R, where R is the gas constant and F is the degrees of freedom. We have 3, F is equal to 3 for monoatomic gas, and Cp is equal to Cv plus R, and we substitute Cv and we get Cp as 5 by 2R. So 5 by 2R divided by 3 by 2R is 5 by 3, which is nothing but 1.67. So that is over here. That is how we are getting, oh my god. That is how we are getting the answer as 1.67. The ratio specific heat capacities for the monoatomic gas is 1.67. I hope it is clear. Now we will see question 14. In question 14, for real operations with the frictional losses, the actual shaft work required is dash. Always smaller than ideal, always greater than ideal, always equal to the ideal, none of the above. So if we are concerned with real operations, we know that actual shaft work is greater than ideal, because efficiency is not equal to 1. Therefore, shaft work is nothing but it is equal to ideal work divided by efficiency. So since efficiency is less than 1, we have actual work to be greater than ideal work. So it is always greater than ideal. Option B is the right answer. We'll see question 15. In question 15, for an axial blower or a two-stage reciprocating compressor, compressor efficiency which is roughly given by dash 0.8 to 0.9, 0.6 to 0.8, option C. Oh, why did it come out here? For an axial blower or a two-stage reciprocating compressor, compressor efficiency is roughly given by 0.8 to 0.9, 0.6 to 0.8, 0.55 to 0.75. Option D 0.45 to 0.65. Answer is 0.8 to 9. 0.8 to 0.9. Option A is the right answer. And efficiency is 0.55 to 0.75 for a turbo blower, 0.6 to 0.8 for roots blower, 0.8 to 0.9 for an axial blower or a two-stage reciprocating compressor. So the question is for an axial blower or a two-stage reciprocating compressor. Therefore, the compressor efficiency is given by 0.8 to 0.9. If it is 0.55 to 0.75, what it is? It is a turbo blower. Or if it is 0.6 to 0.8, it is roots blower. So the question can come in any form. So you get to know these things as well. So as far as our question is concerned, for an axial blower or a two-stage reciprocating compressor, it is 0.8 to 0.9. Option A is the right answer. Now let us look at question 16. In question 16, it is mentioned that determine the compressor power to pass reactant gas into the plenum of the fluid bed system. P1 is equal to 101 kilopascal and P2 is equal to 388 kilopascal. Volumetric flow rate of fluid is 10 meter cube per second. Efficiency of the compressor is 90% and ratio of specific heat capacity is 1.4. That is gamma is 1.4, and we need to determine the compressor power to pass reactant gas into the plenum of the fluidized bed. For that we have P1 is 101 kilopascal, P2 is 388 kilopascal, and volumetric flow rate of fluid is 10 meter cube per second, and compressor efficiency is 90%. As we have seen, compressor efficiency is always less than 100% in the real cases, and specific heat capacities ratio is given as 1.4. So first let us look at the option first. Option A 1927 kilowatt. Option B it is 1820 kilowatt. Option C 1727 kilowatt. Option D 1620 kilowatt. So we'll see how to calculate. I think answer is 1820 kilowatt. We'll see the solution. First, let us write given. So P1 is given as 101 kilopascal, P2 is given as 388 kilopascal, and volumetric flow rate of fluid is given as 10 meter cube per second, and compressor efficiency is given as 90%, and gamma is 1.4. What are we asked to find? Compressor power to pass reactant gas into the plenum of the fluid bed system. And now we need to know the formula. Ws ideal is equal to gamma by gamma minus 1 P1 V1 into P2 by P1 whole power of gamma minus 1 by gamma minus 1. So we are first finding Ws ideal. So gamma we know it as 1.4 and gamma minus 1 it is 1.4 minus 1. P1 we know 101 kilopascal, so 101 into 10 power 3 into V1 is 10 meter cube per second, so it is 10, and into P2 is 388 kilopascal divided by 101 kilopascal to the power of 1.4 minus 1 divided by 1.4 minus 1. So we are getting it as, okay, it is 3.5 into 101 into 10 power 4 into this whole term is 1.4689 minus 1. So we are getting the value as 165789.75, or it is 1657.689 kilowatt. But in question it is given compressor is operating at an efficiency of 90%. So actual shaft work or the compressor power required is to be divided by efficiency. So it is 1657 divided by 0.9, that is 90% efficiency. So it is 1841.8 kilowatt. It would be some numerical error from which I did. So if you calculate it correctly, you will be getting 1820 kilowatt, which is what is the right answer given in the question. So we are asked to determine the compressor power to pass the reactant gas into the plenum of the fluidized bed system. So we have P1 is 101 kilopascal and P2 is 388 kilopascal, and volumetric flow rate is 10 meter cube per second, and efficiency is given as 90%, and gamma is given as 1.4. The answer is 1820 kilowatt. How did we do? We first written the given everything. P1 is 101 kilopascal and P2 is 388 kilopascal, and V1 is 10 meter cube per second, and efficiency of the compressor is 90%. Eta is equal to 90 and gamma is 1.4. So we are asked to find the compressor power to pass the reactant gas into the plenum, and for that we are using the formula Ws ideal is equal to gamma by gamma minus 1 into P1 V1 into P2 by V1 whole power of gamma minus 1 by gamma minus 1. So we know everything in this particular equation, so we are just substituting it. Gamma is 1.4 by 1.4 minus 1. P1 is 101 kilopascal and V1 is 10 meter cube per second, and into 388 P2 by P1 101 to the power of 1.4 minus 1 divided by 1.4 minus 1, and we are getting the answer as 1657.69 kilowatt. Some numerical issues might be over here, please check it for yourself. And this is ideal, but we need to know the exact one, so we are dividing it by the efficiency of the compressor. So 1657.69 divided by 90% efficiency, that is 0.9, and we are getting the value as 1841, which is closer to 1820 of all the values, but some numerical issues will be there. So answer is actually 1820 kilowatt, that is the right answer. So that is what we did. I hope it is clear now. We'll go to question 17. Question 17, it is asked that bubble rise velocity exceeds its linear growth and increasing orifice flow, bigger bubbles form. Okay, bubble rise velocity exceeds its linear growth rate and increasing orifice flow, bigger bubbles form. Dash. Above single orifice, above perforated plate, at a nozzle tuer, none of the above. So we have seen that bubble rise velocities exceeds its linear growth rate and further increasing the orifice flow, bigger bubbles form. This happens with single orifice. So when we have a single orifice, we have that the bubble rise velocity exceeds its linear growth rate at a certain height, and also the further increasing the orifice flow rate, bigger bubbles tends to form. It is asked in which of the distributor, that is whether it is above the single orifice or it is above perforated plate or above a nozzle tuer or none of the above. So answer is actually above the single orifice. Answer is option A. Now we'll see question 18. In question 18 it is given that ratio of specific heat capacities for the diatomic gas is dash. So in the last problem, we have seen how to calculate the ratio of specific heat capacities for a monoatomic gas. Gamma is nothing but Cp by Cv, where Cv is equal to F by 2R. F is 3 for a monoatomic gas and Cp is equal to Cv plus R. And for the substitution, we found it as 1.67. But for diatomic gas, what is the case? Option A 1.33, option B 1.4, option C 1.67, option D 1.85. I think 1.4. Option B 1.40 is the right answer. We'll see how it is 1.4. For diatomic gas, F is equal to 5. That is, we have 3 translational degrees of freedom and 2 rotational degrees of freedom. So, uh, it is, how to say, F by 2 R. So here we have 5. So 5 by 2 R, Cv is equal to 5 by 2 R. And Cp is 5 by 2 R plus R. So it is 7 by 2 R. So Cp by Cv, it is 7 by 2 R divided by 5 by 2 R. 7 by 5. So 7 by 5, it is 1.4 is the right answer. So thing is, what you need to be careful enough is that you need to know the degrees of freedom for monoatomic gas and diatomic gas, or you should just memorize these values for specific heat capacities for diatomic gas and monoatomic gas. Gamma is equal to 1.4, we all know. For diatomic gas we use everywhere, but for monoatomic gas it is 1.67. That also you should be careful. Why? Because it is simple calculation. Cp gamma is equal to Cp by Cv. Cp is equal to Cv plus R. So you can also say Cv plus R divided by Cv. So it is 1 plus R by Cv something. That calculation we need not go, but it is Cp by Cv and Cp is equal to Cv plus R and Cv. Cv is equal to F by 2R and F is 3 for monatomic gas. We have only translational degrees of freedom, but for diatomic gas we have 2 extra degrees of freedom, that is rotational degrees of freedom as well. So here it is 3 plus 2, 5. So on that basis we do calculations and we are getting the answer as 1.4. So that is option B, 1.4 is the right answer. Cp is 7 by 2 R and Cv is 5 by 2 R. So Cp by Cv is equal to 7 by 2 R plus divided by 5 by 2 R. So it is 7 by 5, which is 1.4. So answer is 1.4. I hope it is clear. Now let us go to question 19. At higher velocities, bubble coalesce into horizontal jets. This statement is true for dash. A nozzle tuer, a bubble cap tuer, a perforated plate, none of the above. At higher velocities, bubbles coalesce into horizontal jets. I think it is bubble cap. Nozzle tuer, nozzle tuer. At, I mean, if it is, just check for these statements in their notes itself. I'm a bit, I got confused over here. But the answer is at higher velocities, bubbles coalesce into horizontal jets. What type of distributors we are using for us to get this particular condition? That is, at a higher velocities, bubbles coalesce into horizontal jets. In most cases, we have seen that when we are passing higher velocities, those bubbles grow in size and they coalesce with the preceding bubbles. So it would be horizontal, it would be vertical coalescence mostly. But if at higher velocities bubbles coalesce into horizontal jets, this statement is true for which type of distributor? It is nozzle type, nozzle tuer, nozzle type tuer, nozzle tuer. So option A is the right answer. But I would suggest you all to have a complete understanding of what type of distributors is used for which type of purposes and what type of things we are getting out of each distributor in terms of pressure drop, in terms of bubble coalescence, or in terms what happens if you use low velocities, what happens when we pass higher velocities. So all these things, please be careful. It might confuse you when you are dealing with so many things. So before exams and all, please be clear in these concepts. Now the last question for today's session. Calculate the compressor power requirement to run an atmospheric fluidized bed coal combustor when distributor pressure drop is 3 kilopascal. Air enters at 101 kilopascal and 20 degrees Celsius. Gamma is 1.4. Pressure drop across bed is 10 kilopascal. Pressure at the bed exit is 103 kilopascal and coal feed rate is 8 tons per hour and its gross heating value is 25 megajoules per kg. The air at standard conditions needed is 10 meter cube per kg of coal. And efficiency of compressor is 75%, that is it is 0.75. So what are we asked to find? We are asked to find the compressor power requirement for running atmospheric fluidized bed coal combustion. Distributor pressure drop is 3 kilopascal. Delta PD is 3 kilopascal. Air's inlet conditions are given in terms of its pressure and temperature and gamma, and bed pressure drop is 10 kilopascal. Delta PB is 10 kilopascal. Pressure at bed exit is 103 kilopascal and coal feed rate is 8 tons per hour and its gross heating values is 25 megajoules per kg and we require 10 meter cube per kg of coal and efficiency is 0.75. So we are asked to find the compressor power requirement. The answer is option A 455 kilowatts, option B 655 kilowatts, option C 355 kilowatts, option B 200 kilowatts. Answer is 455 kilowatts. We'll see that how. So we have P0 is given, P3 is given, that is exit pressure, and P0 is 101 kilopascal. We are sending air, and T0 also we know. So here it is the compressor, and here if it is P1, if it is P2, and this is P3. So given pressure drop, distributor pressure drop is 3 kilopascal. Air inlet conditions P0 and T0 is given, which is 101 kilopascal and 20 degrees Celsius. Gamma is 1.4. Pressure drop across the bed is 10 kilopascal. Pressure at bed exit P3 is 103 kilopascal. Coal feed rate is 8 tons per hour. Coal gross heating value is 25 megajoules per kg. And air at standard conditions required is 10 meter cube per kg of coal. So for 1 kg of coal, we require 10 meter cube of air. If that is the case, how much we require for 8 tons per hour? We can get the volumetric air flow rate also from these two statements. And efficiency of the compressor is 0.75. We are asked to find the compressor power requirement. So first, we are directly jumping into solution because it is a series of steps we require. So first one is P3 is 103 kilopascal, P0 is 101 kilopascal, and V0 is and V0 is Q into M. So Q is the volumetric flow rate of air we require. It is 10 meter cube per kg. It is not given directly in terms of meter cube per second. So it is given as 10 meter cube per kg. And M is the mass flow rate. It is 8 tons per hour. So 1 ton is 1000 kg. So 8 tons per hour is 8000 kg per hour. And what are we getting? Kg and kg get cancelled and we are left with hour. We need 18 meter cube per second. So we are again dividing by 1 hour as 3600 seconds. So hour per second. So again it is 1 hour, and hour gets cancelled and we are left with seconds. So we are getting meter cube per second. So it is 22.22 meter cube per second at standard condition. And V0 at 20 degrees Celsius is, we need to get the value at 20 degrees Celsius. So here it is we are multiplying and by 293 divided by 273, and we are getting it as 23.85 meter cube per second, and bed pressure drop is 10 kilopascal. P2 is be unknown, but P3 is 103 kilopascal. So here it is P2 means 103 kilopascal. So we have 10 kilopascal pressure drop from here to here. So what would be P2? P2 is 113 kilopascal, right? 103 is exit and it has 10 kilopascal pressure drop, and to get the P2 it is 103 plus 10, so it is 113. Again distributed pressure drop we know it is 3 kilopascal, so therefore it is 113 plus 3 116 kilopascal. So compressor exit pressure is 116 kilopascal. So I hope it is clear now. We are for us to get the compressor work done, we need to know the inlet and the outlet conditions of the compressor. So inlet condition is that air enters at P naught 101 kilopascal and T naught at 20 degrees Celsius, and we are not given V naught. For that it is given standard condition we require 10 meter cube per kg of coal, and for us to get the compressor work power requirement we need to know what is the exit condition from the compressor power. So we aren't given it directly, rather it is given in terms of these things. So here it is, we'll see it in the next slide. So here it is 101 kilopascal, and V naught we have calculated by using this particular formula, where it is 10 meter cube per kg of coal. We are dealing with 8 tons per hour, so it is 8000 kg per hour, because 1 ton is equal to 1000 kg. So 8 tons is equal to 8000 kg per hour, and again this hour we are converting into seconds, so it is 1 by 3600. So on the whole we are getting it as 22.22 meter cube. So to get the values at standard conditions, because I mean at 20 degrees Celsius, because P naught is at 20 and T naught is at 20 degrees Celsius. So we need V naught at 20 degrees Celsius. So we are getting 22.22 into 293 divided by 273. We are getting this volume of air, I mean volumetric flow rate of air as 23.85 meter cube per second. Now P naught, V naught, T naught we know, but exit conditions we don't know anything. That is, we need to know P1 at least, right? Exit pressure from the compressor. So for getting P1, what are we given? We are giving the pressure drop of the bed, we are given the pressure drop of the distributor, and we are giving the exit pressure. If it is 103 and this particular pressure drop is 10 kilopascal, we know the P2 becomes 103 plus 10. So it is 113. Again we know the bed distributor pressure drop as 3. So it is 113 plus 3 116. So here it is P2 minus P3 is equal to 10 kilopascal. P2 is equal to 103 plus 10 113 kilopascal. Again distributor pressure drop is 3 kilopascal. P1 minus P2 is 3. So P2 is 113. So P1 is 116 kilopascal. So compressor exit pressure is 116 kilopascal. That much is clear from these slides. Now we are going to P naught. We know now P naught is 101 kilopascal. P1 is 116 kilopascal, and V naught is 22.22 meter cube per second. I mean V naught is 23.85. 0.85 meter cube per second, and P1 is 116 kilopascal. So we are going to substitute everything in the formula. W as ideal is equal to gamma by gamma minus 1. Gamma is 1.4, gamma minus 1 is 1.4 minus 1. P naught is 101 into 10 power 3 kilopascal into 23.85 meter cube per second, and P1 is 116 divided by 101 to the power of 1.4 minus 1 divided by 1.4. And minus 1, and we are getting the value as this one, 3.5 into these values, and 116 divided by 101 to the power of 0.2587 minus 1, and we are getting value as 340 kilowatt, 340.24 kilowatt is what we are getting. And but we know that actual work done or actual power requirement is greater than the ideal condition. So this is the ideal condition. So what do we need to do? We need to divide the value at the ideal condition by the compressor efficiency. So compressor efficiency is given as 75%. So we are dividing 340 to 340.24 divided by 0.75, and we are getting the value as 453.65 kilowatt. So 454 is kilowatt is the right answer. And what have we got in the answer? 455 kilowatt is the right answer. So how did we get? First, we need we are asked to find the compressor power requirement. For that, we need to know the inlet and the exit condition from the compressor. Inlet condition we know P naught, and V naught we need to calculate. T naught is given as 20 degrees Celsius, and P3 we know 103 kilopascal, and bed pressure drop is 10 kilopascal, so it is 113 kilopascal for P2, and distributor pressure drop is 3 kilopascal, so P1 is 116 kilopascal. So P naught, P1 we know, and V naught we need to know. V naught is given as 10 meter cube per kg of coal. We are using coal feed rate as 8 tons per hour. So it is 8 tons per hour. 10 meter cube by per kg of coal into 8 tons per hour. 8 tons is nothing but 8000 kg. So 8000 kg per hour, and again we are converting it into seconds. So it is 22.22 meter cube per second, and at 20 degrees Celsius we are getting the values as 23.85 meter cube per second V naught. And now we know P naught and V naught. P naught and V naught we know, P1 we know. So everything is sorted out. We are substituting in the formula. P once again. Okay. It is standard condition is at 0 degrees Celsius 273 Kelvin, and V naught is 20 degrees Celsius 293 Kelvin. So that is how we got V naught. Now we know P naught, V naught, T naught, and P1. And gamma we know. So everything is known in this particular formula. Gamma we know, P naught we know, V naught we know, P1 by P naught we know, gamma minus 1 by gamma. So substituting everything, we have the ideal power requirement as 340.24 kilowatts, but we are not dealing with ideal power. I mean, we don't want ideal thing, we want to the actual power requirement. So we are dividing the ideal power requirement divided by the compressor efficiency, which is giving us 454 kilowatt. So that is the answer, also 455 kilowatt. Calculate the compressor power requirement to run an atmospheric fluidized bed cool combustor. So now we got the values. So that's it for today's class. If you have any doubts, you can ask. If not, we can meet in next class. That is for today's class. We'll meet again at next Saturday, same time, 3 p.m. to 5 p.m. And close the session if there are no doubts. If there are any doubts, we can discuss. Okay, then thank you for coming. We'll see you next week. Thank you.